Okay, part 3. These questions come from chapter 5, the chapter dealing with exponential and logarithmic functions. Question 11, parts A and B are the graphs of exponential functions. This one happens to be exponential growth because its base is larger than 1. This is exponential decay because the base is between 0 and 1. So the steps we learned for graphing an exponential function are to first find a horizontal asymptote, which is determined by the value after the exponential term here, moving the graph up or down. Plus 2 moves the graph up 2 units, which also moves the horizontal asymptote up 2 units. And the next step is to find the y-intercept by letting x equal 0. If x is 0, 0 minus 1 is negative 1. 2 to the negative 1 is 1/2. 1/2 plus 2 is 2.5, which is about right there. Now to complete the graph, we need some more points. Now this is an exponential growth function, which means the graph from left to right is very, very close to the horizontal asymptote, but it continues to increase rapidly as x gets larger and larger. So we want to find the x values over here to give us a good idea of the rate of increase, or how the graph is increasing. So choose x values beyond 0, x equals 1, x equals 2, or x equals 3. If x equals 1, we get 2 to the 0 plus 2, which is 3. So 1 comma 3. If x equals 2, 2 minus 1 is 1. 2 to the 1 plus 2 is equal to 4. So 2 comma 4. If x equals 3, 3 minus 1 is 2. 2 squared is 4. 4 plus 2 is 6. This is a graph of that shape. Very similar on part B, we start with this number to find our horizontal asymptote. It's negative 1. Okay, now we use x equals 0 to find our y-intercept. If x is 0, 1/3 of the 0 is 1. 1 minus 1 is 0. Now since this is a decay function, the graph from left to right is decreasing. Okay, the y values are getting smaller. So I want to choose x values on the left side of the y-axis so we can get a good idea of how the graph is decreasing before it eventually begins to level out. So for our x table, I'm going to choose values on the left side of the y-axis. If x is negative 1, 1/3 to the negative 1 is 3. 3 minus 1 is 2. Okay. And 1/3 to the negative 2 is the same as 3 squared, which is 9. 9 minus 1 is 8. So negative 2 comma 8. This is a graph like that. Okay, 12. A, B, and C we need to evaluate. Evaluate means give the value of the expression. Log base 3 of 81 has a value. Now one of the properties of logarithms that we learned about is a logarithm with a base of 3 would cancel an expression that has a base of 3. So if we can change 81 into 3 to the 4th power, then the log base 3 cancels the base of 3, leaving a 4. So the answer is 4. Same on part B. We need to try to write 5 as 25 to some power. It turns out that 5 is the same as 25 to the 1/2, because any 1/2 power is the same as the square root, and the square root of 25 is 5. So the log base 5, or the log base 25 of 25 to the 1/2. 25, the two bases of 25 cancel, leaving a 1/2. Now the natural log is a logarithm with a base of e, even though it's never written. So a natural log cancels with the base of e, leaving a 3. Okay, expand or condense each logarithmic expression. In this case we're expanding. This is an example of the product rule. Product rule states that if you're taking the logarithm of a product, that can be expanded into multiple logarithms separated by addition. So this is going to be the log base 4 of x squared plus log base 4 of y plus log base 4 of z to the third. Now there was another property we learned called the power property. If you're taking the logarithm of an expression that has an exponent, then the exponent can come down to the front of each logarithm. So it's going to be 2 log base 4 of x plus log base 4 of y plus 3 times log base 4 of z. Now when we have multiple logarithms, we're going to condense that into a single logarithm using the power property, the quotient property, and the product property. So if you notice, the last property we applied here was the power property. We brought exponents down to the front of the logarithm. And that's what you do when you're expanding. When you're condensing, that's the one you start with. You start by moving numbers in front of logarithms back up as exponents. All of these numbers in front of the logarithm need to move back up as exponents in the expression. So this is going to be the log of x squared minus the log of y to the fourth plus log z squared. Now condense from left to right. So starting with these two logarithmic expressions, since there's a minus sign between them, that's an example of the quotient property. These two need to be combined, forming a quotient. So log, quotient means fraction, so it's x squared over y to the fourth plus log of z squared. Now these two logarithmic expressions are separated by a plus sign. That's an example of the product property. So we need to form a product now when we condense these two logarithms. Product means multiply. So this is the log. When x squared over y to the fourth is multiplied by z squared, that results in x squared and z squared in the numerator, y to the fourth in the denominator. Solving logarithmic equations. You solve a logarithmic equation by isolating the logarithmic expression and then exponentiating both sides, or rewriting the expression in exponential form. Now this is the exponential term, or excuse me, the logarithmic term, natural log of x plus 3. We need to get this all by itself. So that means we have to add 2 to both sides. So we're going to have the natural log of x plus 3 is equal to 5. Now the natural log, again, has a base of e. If we rewrite this in exponential form, this is our base e. The 5 acts as the exponent, and the x plus 3 is no longer inside of a logarithmic function because we've rewritten this in exponential form. Now, last step to isolate x is to subtract 3 on both sides, so x is equal to e to the fifth minus 3. Now when you have a logarithmic equation with multiple logarithms, you need to condense the logarithms into a single logarithmic expression. So these two logarithms here are separated by a plus sign. This is another example of the product property. So when you condense these two logarithms, the two expressions, x minus 2 and x, need to form a product. That product would be x squared minus 2x if you multiply those together. Now we have a single logarithm. This can be rewritten in exponential form. Now 2 is the base, 3 is the exponent, and the x squared minus 2x is no longer inside of the logarithmic function because we've rewritten this in exponential form. Now if we set this equal to 0, by subtracting 2 to the third is just 8. So subtract 8 on the other side, factor and the two zeros, or the two solutions, are x equals 4 and x equals negative 2. Now, a critical mistake here is to remember the domain of a logarithm. The domain of a logarithm are numbers greater than 0. You can't, when you plug a number into a logarithmic function, that can't result in a negative number. So for example, if I took the negative 2 and plugged it in for this x, you can't take the logarithm of a negative number. That's impossible because it's not in the domain. So negative 2 is actually an extraneous solution. X equals 4 is the only solution to this. Okay, question 15 here. This is an exponential equation that needs to be solved using logarithms. But before the exponential can, before a logarithm can be used, this exponential term right here, 2 to the x plus 2, needs to be isolated. So we're going to add 1. We have 4 times 2 to x plus 2 equals 12. Now divide by 4. And we have 2 to the x plus 2 is equal to 3. Now we can take a natural log. We can take any logarithm, really, natural log, but probably the logarithm we want to use is a log base 2. Because that cancels that base of 2. So what we have is the equation now, x plus 2 is equal to the log base 2 of 3. Now subtract 2, and remember that 3 is inside of a logarithm function, so 2 cannot be taken from it. So the answer, x equals log base 2 of 3 minus 2. Okay, question 16 here. The half-life of palladium-100 is 4 days. After 20 days, the sample has produced a mass of 0.375 grams. What was the initial mass of the sample? This is referring to the function a of t is equal to a sub 0 equals e to the power of kt. What they're asking for is a sub 0, this initial mass. Now we don't know this k is called the growth factor. But we know that at time equals 20 days, there's 0.375 grams. So there are a couple of ways we could find a sub 0. We could use the fact that a half-life is 4 days. So regardless of the starting amount, after 4 days, half of that is going to be remaining. So we could set a sub 0 to be anything we want, and if we let time, or the value of t, be 4 days, then half of that is going to be remaining. So if we did let t equal 4, regardless of the initial mass, after these 4 days have passed, half of it's going to be remaining. So if we took the initial mass and divided it by that half that was remaining, we would get a value of 1/2 right here. Now what we're doing is solving for k, which I know part A isn't asking for, but it's going to help us find the initial mass if we know the value of k. So if we solve for k, now we can do that by taking a natural log. Natural log and a base of e are inverse functions, so they cancel each other out. So what we have is natural log of 1/2 is equal to k times 4. So if we divide by 4, we get k is equal to the natural log of 1/2 over 4. Now that we know the value of k, we can say, okay, when time equals 20 days, there's 0.375 grams remaining. Because all of this has to be done by hand, 0.375 is going to be much easier to deal with if it's a fraction. 0.375 is 375th 1,000th. So if you went through the process of simplifying this, you would simplify it down to 3/8. So 3/8 would be an a of t value if t is equal to 20. So we could say that 3/8 is equal to the initial amount, which we don't know, times e to the natural log of 1/2 divided by 4, and then we let time equal 20 days. Now 20 over 4, those can reduce to 5. And then e to the natural log cancel out, which means the 1/2 can drop down as a number. This 5 has to stay as an exponent, but this 1/2 can drop down as a base. So we're going to have 1/2 to the 5th power. 1/2 to the 5th power is 1/32. And then if we multiply by 32 on both sides, and those are going to cancel. Now we've isolated a sub 0. And then over here, 8 goes into 32 4 times. 4 times 3 means that a sub 0, the initial mass is 12 grams. We've accomplished actually 2 things here. Not only have we answered the question, what's the initial mass, 12 grams, we also have solved for the value of k, which we would have had to do here anyway, in part B, because now they're asking for a function that models their mass remaining after any amount of time, t days. So a of t is equal to 12 times e natural log of 1/2 over 4 times t. Now there is another way that at least part A could have been done. Because the half-life is 4 days, and 20 is a multiple of 4, so in 20 days, how many half-lives have occurred? Well, there's 5 half-lives. Each time a half-life occurs, it gets cut in half. So if we track backwards, instead of allowing time to move forward and cutting the substance in half, if we track backwards through the half-life, we're actually going to double it 5 times. So if you take 3/8 and then double that 5 times, that's going to be times 2, times 2, times 2, times 2, times 2, but that's just 2 to the 5th, and that's just 32, and we would have gotten the same thing, 12 grams. Now I know that seems like a much easier way than how we did this in part A. This method only worked because this 20 days happened to be a complete multiple of 4. Now, question 17, using this formula, this is the formula to find the pH of a substance. Some kind of a substance has a hydrogen ion concentration of 1.6 times 10 to the negative 5. We got to find the pH. So using the formula, pH is equal to the negative log of the hydrogen ion concentration, and that's 1.6 times 10 to the negative 5. Now, we're going to have to use the product property of logarithms here, because we're taking the logarithm of a product. It's this same as this. Log of a times b is the same as the log of a plus log of b. This is the product property. So this is going to be negative. Now we're going to expand this logarithmic expression into the log of 1.6 plus log of 10 to the negative 5th. Now this negative 5 can drop down in front of that logarithm. And then we're taking this log, which has a base 10 of 10, so those cancel each other out. And if we distribute this minus sign, we're going to end up with negative log of 1.6 plus 5, and this is equal to the pH. Unfortunately, since I'm not using a calculator, that's as far as we can take that calculation. Part B, we're going the other way. We know the pH. We want to find the hydrogen ion concentration. So pH value of 2 is equal to the negative log of the unknown H plus value. Now if we divide by negative 1 here, we have negative 2.8 is equal to the log of hydrogen ion value. If we raise both sides to the power of 10, or if we raise both sides using a base of 10 rather than that base of 10, and that logarithm is going to cancel, leaving what we were trying to solve for, H plus then is equal to 10 to the power of negative 2.8. Okay, question 18, part A and part B, we're solving systems of equations here involving 3 variables. The suggestion I made here is, if at all possible, try to avoid eliminating z as a first step. Simply because if there are infinitely many solutions, then it makes parameterizing them here a lot more difficult, at least according to convention. So on part A, And notice here that we have a value of 2y and a value of 2y. So if you multiply the top equation by -1, you get negative x minus 2y plus 2z equals -1. Middle equation can stay the same, 2x plus 2y minus z equals 6. If we add those, y's cancel, and you're left with x plus z equals 5. Now, we have to repeat this and eliminate y again from 2 more equations. So if I take this middle equation, multiply by -2, that's going to put a -4y right here, which will cancel with that 4y. So the middle equation becomes -4x minus 4y plus 2z is equal to -12. Bottom equation is 3x plus 4y minus 3z equals 5. Now, y cancel, and we have -x minus z equals -7. If we now take these two equations in terms of x and z and combine those, we end up with this statement, 0 equals -2, which is not true. Therefore, we would say no. Solution. Now, if it had happened that these were also opposites of each other, and the numbers cancel, these constants cancel, then 0 would equal 0. In that case, there would be infinitely many solutions. We'd have to parameterize. Here on part B, right off the bat, if you notice with these top two equations, we already have opposite coefficients, -2y and +2y. So if we just take these two equations here and add them together, we're going to get 2x, the y's would cancel, plus 2z, and that's equal to 14. And if we take the top and the bottom equation, we also have opposite coefficients, -2y and +2y. So if those are added together, we get 4x minus 2z is equal to 4. And right off the bat, z's, I mean, this works out kind of nice. I wouldn't expect the ones on the final maybe to work out so nicely. But the z's cancel right off the bat, and we have the equation 6x equals 18, so x is equal to 3. Now you have to work your way back through the steps. We can't take just one x value and go all the way back to the beginning equations. If we know that x equals to 3, then taking this middle equation, for example, 2 times 3 would make this 2x turn into a 6. So we have 6 plus 2z is equal to 14. If we subtract 6 on both sides, 14 would turn into 8. So you'd have the equation 2z is equal to 8. Divide by 2 and you get the value that z is equal to 4. Now if we take both of those to the original equations, this middle one for example, we know that x is equal to 3. We don't know the value for y, but we know that z is equal to 4, so that's minus 4 is equal to 13. 3 minus 4 is -1, so -1 plus 2y is equal to 13. If you add 1 there and add 1 there, that becomes a 14. If you divide by 2, you get y is equal to 7. So your solution is the ordered triple 3, 7, 4.